area of a parallelogram's formula is something that you guys have used before. You probably saw it more in the terms of a rectangle, when you have area equals length times width. In an area of a parallelogram, we're going to convert that so that it works for all parallelograms, not just a rectangle. And we're going to do that by making the formula area equals base times height. Now the key to this is that the base and the height are always in a perpendicular relationship, no matter how they're drawn. Up a little bit. So you could have your base down here and your height that way. We'll change colors here. This could be your base and your height could go that direction. There's really no set rhyme or reason to this. The key is you guys have probably been trained pretty well that the base is usually the bottom, but that's not always true. What you are looking for is the right angle, whether it's here, or even outside of the parallelogram itself. But the right angle is the key to know where your base and your height are. So let's take a look at why this formula works. Here we got a parallelogram on a graph. I'm going to just grab over here this triangle off the edge. Now if I take that triangle off the edge and I move it over to the other side, what that creates is that rectangle that we were looking at before, so that we have our base down here and our height here with a right angle. Now, what is true about this is I can take this length right here, which is the length of 7. If I were to draw that length of 7 anywhere I want on the same level, so that's 2, 4, 6, 7 right here, and connect it down to that base, we're not changing the area of our parallelogram at all. It's kind of a nifty little deal where I could take this length right here is 7, move it left or right wherever I want, as long as I stay on the same level, keeping the base the same, our area will stay consistent the entire time. A sample problem of what we're going to be looking at here could be a problem like this. They give us the two measurements of a parallelogram. The bottom here is 12. The other side is 10. We need to find the area of this parallelogram. We would start off with our formula. Area equals base times height. I'm going to use our base here as our 12. They give us a huge hint right here with the 60-degree angle. When they give you a 60 or a 30 or a 45 in this position right here, they're referring to your special right triangles, your 30, 60, 90s, or your 45, 45, 90s. They give you a different angle. What they're hoping you do is use some trigonometry in here. But being that you have a 60-degree angle, they want you to focus on your 30, 60, 90 right here. So according to our 30, 60, 90 rules, this is 2x, 1x, and x root 3. So if this is 10, we have 5 right here, which gives us the height of our parallelogram at 5 square root 3. So the area of our parallelogram, 12 times 5 gives us 60 times the square root of 3. We're going to load up our calculator here. and we're going to go with 60 times the square root of 3, and we're going to get our answer here, which is 103.9. And our area would be in units squared. When we're dealing with area, we're always talking about square units. Here's the sample of a graphing type of problem. They ask you to find the area of a parallelogram with the following coordinates and then list out A, B, C, and D. I've prepped this a little bit here with the A, B, C, and D already marked. My suggestion to you is to always use your horizontal and vertical lines when you're trying to find an area on a coordinate plane. So with that being said, we have a horizontal distance right here that is a length of 6. And then from there, we can pick any perpendicular we want that goes from base to base. It doesn't have to be just there. It could be anywhere along here, even outside if we want. So looking right here, we have a height that is a height of 2, 4, 5. We got a height of 5. Area is base times height, which would be 6 times 5. And we're looking at an area that is 30 square units. You will run across some unique different types of shapes that they're going to ask you to find the area of. And what you have to understand on these is the idea that finding the area of this type of shaded region is really addition problem of a whole bunch of parallelograms together. My suggestion to you, if you get completely stuck on something like this, is to take a piece of graph paper and actually graph it out. So we can see on this I'm a little bit sloppy here, so forgive me for that. That's basically our shape right there. Every box, because all the corners are square, are actually squares. And remember that area is really the summation of all the squares that you have here. So we could block this off into rectangles. Right here I got a 2 by 8, which would give us an area of 16 down here. I got a 2 by 4 right there, which would give me an area of 8. Up here I have a 2 by 8. Ooh, that doesn't sound right. 2, 4, 6, 8. That'd be 16, which means down here, I think I miscounted. Okay, so 2, 4, 6, 8, 9. That would have been 18. And we got an area right there of 2. So if I add all these up, 18 and 2 would give me 20. This would be 36 plus 8. That would be 44 square units. There are some unique problems on your homework assignment like this one, where you got a rectangular poster with measures of 42 by 26. The frame shop fitted a poster with a 1/2 inch border or map border. Find the area of the map border. So what you're looking at here is truly this. You have your poster. It is 42 by 26. They put a map border around the outside of it. It's a 1/2 inch in every direction, which means it's 1/2 inch that way, 1/2 inch that way, which means that 42 is now 43 inches. It's a 1/2 inch that way, 1/2 inch that way. which adds a full inch to the 26, making it 27 inches that direction. To find the area of the matting going all the way around this, what we're going to do is we're going to take the area of the large rectangle, subtract it from the area of the small rectangle. So our large rectangle would be 43 times 27. Our small one is 42 times 26. So 43 times 27 gives us 1,161, and 42 times 26 gives us 1,092. We're going to take our two answers here. A little extra there. And we're going to go ahead and subtract them. And that gives us an answer of 69. So we got this is equal to 1,161, 1,092 for this one. And if we subtract those, you got 69 square units. So that would be the area of the matting. The next part of our lesson is on area of triangles, trapezoids, and rhombi. So we're going to focus first on the area of triangles. We should have all heard by now that the area of a triangle is 1/2 base times height, or base times height divided by 2. They are the same formula, either way you look at it. Same thing holds true with triangles as with parallelograms, where the base and the height have to be a 40 or a 90-degree angle with each other. So it could be a base and a height like that. You could have base and height that way with a right triangle, or the base and the height could be outside of each other. Be careful on this, that the base only goes from that point to that point, and your height is out here. This shows you that the base and the height do not need to be connected with each other. Sometimes they are separated when the height is on the outside of the triangle, but they are still perpendicular to each other. Now let's take a look at why this is true. If I were to draw a generic parallelogram on here, just any old parallelogram I want, and I draw in a diagonal, I can see here that that diagonal cuts the parallelogram into two congruent triangles, basically because of side, side, side. This triangle right here, triangle number 1, is the exact same as triangle number 2. Because the area of the parallelogram is base times height, we only want half of it because we got two congruent triangles. The area of every single triangle is exactly 1/2 base times height. Now if I go back to this slide, any one of these triangles that I duplicate and I rotate over, I can make into a parallelogram in this type of alignment. So let's take a look at some problems. If triangle ABC has an area of 48 square inches and a base of 12, what's the height of triangle ABC? Well, I'm going to start that off by drawing a triangle. It doesn't really matter what type of triangle it is that I'm looking at. I know the base here is 12. We're looking for the height, and we know that the area is 48. So I'm going to start off with my formula. Area equals 1/2 base times height. I'm going to plug in what I know. It is important that you have both sides of our equation here. We're going to plug in the 48 for the area. We're going to plug in the 12 for the base. We're going to solve for the height. Half of 12 would be 6. We divide by 6. Our height would end up being 8 inches. Now here's the nifty little problem where you're trying to find the area of this quadrilateral. But what you should notice here on this quadrilateral is that this distance right here is perpendicular to that distance and perpendicular to that distance. Now, with that being said, what you really have here instead of a quadrilateral is two different triangles. They both share a height that is 7. Or 8. 1, 2, 3, 4, 5, 6, 7. Sorry, it's a height of 8 right there. That distance there is 8. Over here we have 3. Over here we have 2, 4, 6. So I'm going to find the area of this triangle first. 1/2 base times height. This would be 8. This would be 6. So it's 1/2 8 times 6, which would be 24. Then I'm going to find the area of this triangle. Which would be 1/2 of 8 times 3. That would be 12. So your total area would simply be 24 plus 12, which is a total area of 36. Now for the area of a trapezoid, we're actually going to have two different formulas that I'm going to show you. One is the traditional formula, where the area is 1/2 the height times base 1 plus base 2. And the second formula, not such a traditional formula, is simply the length of the median times the height. Chances are you will see me use just this. M times H, median times height. This could also be, besides median, depending on the author, it might be referred to as a mid-segment. So let's take a look at where this comes from, or these formulas come from. The first one we're going to look at is the traditional form of the equation. What I'm going to do here is I'm going to go just halfway. We're going to cut our trapezoid in half that direction. I'm going to do the same thing up on the top. Now what happens here when I take the top portion and I flip it around 180 degrees and drop it down here, the end result is, in this green portion, is a perfect parallelogram. Now we know that for a parallelogram, area is equal to base times height. So the area of this if we look at the bottom portion of this, here's base 1, here's base 2. The height of this is half of the height of the actual trapezoid, so the height is 1/2 h. The base of it is base 1 plus base 2 in length, and voila, there's that formula. It looks like it just was kind of made up out of thin air, but it actually has some relevance when you look at that trapezoid and redesign it into a parallelogram. The second way you could look at this is using that whole idea of a median. Remember that a median or a midpoint happens when you take the midpoints of the two legs of a trapezoid and you connect them together. So that length right there is the mid segment or the median. This length right here is also the mid segment or the median of that trapezoid. So if we go along our same path here, we have 1/2 the height, because we still have this portion right here which is still in play, but instead of doing base 1 plus base 2, we're doing median plus median, which is 2 medians. Now 1/2 times 2 cancels each other out, and that leaves us with the height times the median or the mid segment as another possible formula that we could use. So we're going to start pretty simple here. We got to, find the area of this figure. They're giving us the two bases and the height, so we're just going to use our traditional formula here. 1/2 the height times base 1 plus base 2. So our height here is 16. Base 1 plus base 2 is 32 plus 18. 32 and 18 add up to 50. Half of 16 would be 8. So we're looking at 400 square units here for this problem. Next problem here, they tell us that the area of the trapezoid is 935. They give us the two bases again, which is the hint that says we're going to use our traditional formula, 1/2 the height times base 1 plus base 2. We're going to plug in what we know. Our area is 935. And it's half the height times 30 plus 55. Now if I were solving this, being that we have all multiplication on the right side here, we're multiplying the parentheses times the h times the half. I would multiply both sides by 2 to start off with to get that 1/2 out of there. So that would give us 1,870 equals the height times 85. And then I would divide both sides by 85. So we're looking at 1,870 divided by 85, and that gives us an answer with a height of 22 centimeters. The third one here that I have is kind of the exception to the rule for using that traditional formula. You can see here they didn't give us the basis. What they did give us, instead of giving us the basis, is they gave us the measurement of the mid segment or the median. So for this one, I'm going to use that secondary formula, the mid-segment or the median times the height. So my area for this would be 32 times 16. And that gives us 512 square units. The last area formula that we're going to look at is the area of a rhombus, square, or a kite. Now we already talked a little bit about squares because a square is a parallelogram, but in this case we would use this area formula that I'm going to show you right now if they were giving us some part of the diagonals of a square. Really what you would do is you would use this anytime you have a quadrilateral with perpendicular diagonals. The formula that we're going to use here is 1/2 diagonal 1 times diagonal 2. Let's take a look at where this comes from. Here I have a kite, or not a kite, but a rhombus all set up for you. We're going to draw in one of the two diagonals. What that does is that breaks up this rhombus into two isosceles triangles. Then what I'm going to do, change colors here. I'm going to drop this one down. I'm going to draw in the height of those two isosceles triangles. Now for this top isosceles triangle, what we have is a formula for that area, which is 1/2 our base, which is in common for both of them, times height number 1. That's the height of the top triangle. Then down here on the bottom, for this other triangle, we have 1/2 the base. It is the exact same base, but this time what we're doing is we're timesing that by height number 2, the bottom triangle's height. Now if I add these two up, what this would look like is 1/2 base times height 1 plus 1/2 base times height 2. Notice that both of these have the 1/2 base in common. So algebraically what we can do is we can factor that out and get 1/2 the base times that by height 1 plus height 2. Now notice here, height 1 plus height 2 is the length of that diagonal right there. I'm going to call that diagonal 2. Base 1, or the base, is that diagonal of the rhombus, which I'm going to call diagonal 1. And that's where our formula comes in. 1/2 diagonal 1 times diagonal 2. Every single kite, square, or rhombus can use this formula to find the area. So here's an example of a kite. We want to find the area of this kite. Our formula is 1/2 diagonal 1 times diagonal 2. So right here, diagonal 1 would equal 28. 18 plus 10. Diagonal 2 right here would be 24 and 24, which is 48. So for my formula, I'm simply doing 1/2 of 28 times 48. So our area on this one would be 672 square units. So let's say they give us a problem where they want us to find the area of a rhombus with a perimeter of 80 inches and a diagonal of 24 inches. What I would probably start off with here is just drawing a quick sketch of a rhombus. The exact measurements really doesn't matter too much. What matters is where you put your numbers. If we have a perimeter of 80, we know a rhombus has 4 congruent sides. That means each side is 20. Now, being that this is a rhombus and they give us a diagonal here, which is 24, that diagonal that is 24 is cut in half because the diagonals do bisect each other, which means we're looking at 12 and 12. What we need are those two measurements in order to find the second diagonal, because we're looking at using the formula 1/2 diagonal 1 times diagonal 2. Right now what we have for this formula is 1/2 of 24, and we need our second diagonal. Now keep in mind that a rhombus, a kite, and a square, all of them have the diagonals that are perpendicular to each other. So what we have down here is a right triangle, which puts in play possibly using your special right triangles, 30, 60, 90s, 45, 45, 90s, trigonometry, or possibly Pythagorean theorem. If we do Pythagorean theorem here and try to find that length, we would go x squared plus 12 squared equals 20 squared. If we solve through this, what we will find is that we would get an x value of 16. If x is 16, that means this side is also 16. This diagonal is 16 plus 16, which is 32. So now we have enough information to use our formula. We're looking at 1/2 of 24 times 32. That's 384. And that would be the area of that rhombus. Okay, let's say they give you a graph. They ask you to plot some points, and you end up with a drawing similar to this. And they want you to find the area of this kite. What I would do is you got to go with the horizontal and vertical lines. So looking at this, your horizontal distance right here, or sorry, your vertical distance there, your horizontal distance right there are the keys to this. Don't fight against using the horizontal and vertical distances. Use those to your advantage. What you see here is that the horizontal and verticals on this drawing are your diagonals. So you're looking at 1/2, diagonal 1, diagonal 2. The diagonals going this way are 2, 4, 6. So we're looking at 1/2 of 6. The diagonal going this way is 2, 4, 6, 8, 10, 12. Looks like 13 that way. So our area would be 3 times 13, which is a total of 39 square units. And that would wrap up our rhombus, kites,